Hello, everyone. Welcome to this week's Grunge seminar. Today we have one talk and two speakers. Our first speaker will be Professor Mikhail Poluektov. Sorry if I'm pronouncing your name. Who's currently an appointed as a lecturer, assistant professor in mathematics at the University of Dundee in the UK. His research focuses on computational and applied mathematics, covering a large range of models and methods. In particular, his research includes fictitious domain and multi-scale methods for nonlinear partial differential equations, as well as approximation theory methods. His work has been published in journals such as Computer Methods in Applied Mechanics and Engineering. Prior to current appointment, Dr. Poluektov held a senior research fellow at the University of Warwick in the UK. He obtained his PhD from Eindhoven University of Technology in the Netherlands. Also, Professor Andrew Pollard, he's also going to talk. He obtained his PhD in automatic control from St. Petersburg State Technical University in Russia in 1991. After his PhD, he began a professional development of computational software in the field of mathematical modeling. Until 2005, his research mostly focused on audio and video compression algorithms. This was followed by natural language processing and semantic search algorithms. During this time, Dr. Pollard obtained one granted patent and published several research papers. Besides his scientific research, Dr. Pollard also held positions of a software developer and worked in the banking industry for World Bank, Bank of America, and Wells Fargo. Professor Pollard is currently retired and uses his software development experience in freelance programming for open source artificial intelligence. Dr. Mikhail and Dr. Andrew, thank you so much for joining us today. We're all looking forward to your talk, and with this short introduction, you may begin.
Yeah, thank you very much for giving us the opportunity to talk about our research on this Kolmogorov-Arnold models, or as recently popularized networks. Our talk will be split into two parts. I will provide an overview of our developments, which should take about half an hour, and then I'll hand over to Andrew, who will talk about some practical and implementational aspects. Over recent year, you might have seen a lot of hype on the Kolmogorov-Arnold networks. They're pitched as promising alternative to classical neural networks. And news items and blog posts highlight their superior accuracy and interpretability. But above all, the specialists in the field discuss their solid mathematical foundation. There are YouTube videos on Kolmogorov-Arnold networks with over 40,000 views, which is quite a lot for the videos not featuring cats. Popular videos include discussions and speculations whether they will really replace multi-layer perceptrons. All this hype originates from a publication of a paper by a team from MIT, Caltech, and Northeastern University about 12 months ago. But this research topic has a long history with contributions of multiple scientists. We started working on this topic around 6 years ago, and in 2020, together with Andrew, we published an algorithm for constructing such type of models, not too dissimilar from what has been published recently by the MIT team. To understand this machine learning tool, we need to start from 1950s, when Andrei Kolmogorov and Vladimir Arnold proved that any continuous multivariate function can be exactly represented by a composition of functions of a single variable. I will refer to f as the inner functions and to capital phi as the outer functions. The original proof stated the existence, but was not constructive and didn't provide insights into choosing the underlying functions of the representation, given that capital F is known. Subsequent works focused on constructive proofs on algorithms for determining the inner and the outer functions in some form, including approximate determination of the underlying functions. Let me visualize the simple case of a function of two inputs. It can be represented as a network where the inputs enter the set of inner functions, the number of which is exactly defined. The outputs of the inner functions are sent to the layer of the outer functions, which in the end produce the final result. If we work in a setting where the underlying functions are approximate, we cannot talk about the exact representation anymore. It is more correct to refer to to such structure as the Kolmogorov-Arnold model. I denote the model output as y hat, which is a function of the model inputs capital X. Here you see that I wrote the inner and the outer functions separately, introducing hidden variable theta. The key element of the model is that the underlying functions are taken as products of the model parameters and some basis functions. These basis functions are a priori set by the user, thus the model is characterized only by parameters h and g. Note that I prefer using word model instead of network, but the meaning is identical. Here I show the model consisting of two layers of functions, and we'll stay within this setting for now. Various options can be used for the basis functions. One way to define them is to introduce a set of equidistant nodes on the domains of the functions. The basis functions can then be cubic splines constructed such that they are exactly 1 at the corresponding node, are exactly 0 at all other nodes. They can be Gaussians that are exactly 1 at the corresponding node and then they are decaying away from it. Or they can also be piecewise linear functions, which is the simplest possible choice. Having defined the model, let's now proceed to the data modeling problem. We're given a data set of n records. Each record consists of vector input x and scalar output y. The data modeling problem can then be written as finding such parameters h and g of the model that the discrepancy between the model and the real outputs is minimized. It is a minimization problem, and various minimization methods can be used. However, care must be taken because first, it's nonlinear with respect to the parameters. Second, it does not have a unique solution. If you're interested in some analysis that we did for this problem, please talk to me after the presentation. Due to the properties of this problem, our preferred method of choice is the Newton-Kaczmarz method. Before I can explain it, I must introduce the simpler version of it, the Kaczmarz method for solving systems of linear equations. It is also known as the projection descent method. Consider linear system mz equals y, where m is the matrix and z is the unknown vector. The method consists in iterative updates of vector z while going through the linear system line by line. Here mi is the ith row of matrix M. The easiest way to understand this method is to visualize it for a system of size 2. In this case, there are two linear equations corresponding to two lines on a plane, with the solution being the intersection point. The method starts with an initial guess, and the point is sequentially projected onto the lines, converging to the solution. The great feature of the method is that for underdetermined systems, it converges to the solution that is closest to the initial guess. Again, consider the underdetermined system of size 2. In this case, both equations correspond to one line, and the projection of the initial guess results in the closest solution. For underdetermined system of arbitrary size, one should think of an infinity of solutions living on a flat subspace, and the iterative process sequentially decreases the distances to all points of this flat subspace. The Newton-Kaczmarz method is a technique for solving systems of nonlinear equations. The approach is iterative. Assuming that the solution at iteration q is known, one can write the ith equation of the system for the solution at iteration q plus 1. It is then linearized with respect to the solution increment delta z. Neglecting higher order terms results in a linear equation which allows us to apply one step of Kaczmarz method. And the latter gives the iterative formula for the solution update. In the formula, I introduced the numerical damping parameter mu, which in machine learning literature is also called the learning rate. When the Newton-Kaczmarz method is applied to the problem of determining the parameters of the Kolmogorov-Arnold model, the resulting iterative formula contains the update of the parameter values in the direction of the derivative of the model with respect to the parameters, and it is proportional to the residual and inversely proportional to the normalization factor. This is done both for the parameters of the inner functions and the outer functions. And the normalization factor is the squared norm of the model derivatives with respect to the parameters. As you see later, such training method performs well. However, there is one conceptual challenge related to this approach. It is not straightforward to parallelize its implementation. This is due to the model's output and derivatives changing each iteration as the parameter updates are performed. One can formally write this as output being a function of the parameters with the current step values used in the iterative formula. This requires iterations to be performed sequentially. However, for non-trivial basis functions, such as splines, by far the largest computational cost is the evaluation of the basis function values. And this can be parallelized. The idea is to linearize the model's output with respect to the parameters taken at some particular step denoted here as omega. Due to the linearization, the model's output and derivatives are now calculated at some parameter values, the same parameter values for large batch of data records. This can be easily parallelized, splitting the full batch into sub-batches for which the evaluations are performed on different cores. In practice, such freezing of the parameter values can be done, for example, for each pass through the training dataset. Of course, the same is done for the parameters of the outer functions. The brilliant thing about the Kolmogorov-Arnold model and the training method based on the Newton-Kaczmarz algorithm is that they can be implemented in elementary code. One of our codes is written in MATLAB, and the core part constitutes fewer than 100 lines. It uses only built-in MATLAB functions and doesn't require any add-ons. The code is so compact that I can fit it. I can fit the main part of it on a single slide. If you're interested, you can find it on our GitHub page. I will now show one numerical example using synthetic data. Usually researchers test models on various kinds of algebraic formulas, while I like the examples that can be easily visualized. Therefore, I've taken an example where one would like to model the area of a triangle knowing the coordinates of the vertices. Of course, in the real world, no one would solve such a problem directly. It would require remapping or the inputs to descriptors, which are invariant with respect to translation, rotation, and the permutation of the vertices. But for the sake of benchmarking, let's solve this problem directly, which makes it a challenging task. When the code is executed with different random initial guesses for the parameters, on average, logarithmic convergence can be observed. The logarithm of the error linearly decays with the logarithm of the number of passes through the dataset. Decrease of the learning rate makes the result less sensitive to the initial guess. And with the optimal value of the learning rate, the approximate error of 5% is achieved in about 300 passes, which is good enough for this challenging problem. If you heard about the Kolmogorov-Arnold networks before, you also probably know that the MIT team has rolled out their Python code together with the publication of their paper. They had a number of benchmarks in their paper, the first of which was function fitting. If we take this benchmark and compare the model's training time in our code and their codes, the difference is quite drastic. Our code is around 40 times faster, while simultaneously being almost 3 times more accurate. The same benchmark problem can be solved by a neural network that is trained to the same accuracy. In the paper, the MIT team has concluded that although the Kolmogorov-Arnold networks have many advantages, the main disadvantage is that they are slow. You can see that this is not true. Our code consistently outperforms neural networks when trained to the same accuracy. Here is another function fitting example where our C++ code is 4 to 8 times faster than MATLAB's built-in neural network. If you're interested in details of the comparison, please talk to me after the presentation. The Kolmogorov-Arnold model is not only fast and accurate, but it's also scalable. The largest example that we considered was training a regression model for a data where the input is 5 by 5 matrix and the output is the determinant of the matrix. The training dataset consisted of 10 million records. Neural networks can be trained on such data, but it requires more than 5 hours on a high-performance laptop. For this comparison, we used the state-of-the-art implementation of the neural networks in MATLAB. Here I plot the accuracy of the resulting model evaluated on the validation dataset versus the training time. When the number of layers and the number of neurons per layer is varied, some performance improvement of neural networks can be gained. However, when the Kolmogorov-Arnold model with piecewise linear basis functions implemented in our code is trained on this data, the difference is again drastic. Not only is it up to 50 times faster, but it is also more accurate. The performance of the Kolmogorov-Arnold model is also robust with respect to the hyperparameters. Variation of the number of the inner and the number of the outer basis functions within large ranges still leads to excellent results within minutes of training. It's only when the number of add-ons is significantly decreased the accuracy drops noticeably. Furthermore, neural network training utilized up to 50 gigabytes of memory and 4 cores, while our code's memory footprint was below 3 gigabytes and used strictly 1 core. A non-parallel version was used here. An example that I just showed was obtained using the basic version of our C++ code. In the more advanced version, we have introduced a number of additional tricks. The algorithm updates the parameters record by record, and if applied straightforwardly, the model's architecture stays constant throughout the entire training. However, it's not necessary to keep it constant. It's possible to start from a coarse model consisting of minimal number of basis functions and increase the number of basis functions each time a certain number of iterations is completed. When the number of basis functions is changed, the parameters must be resampled, but this is a straightforward step. Such strategy is particularly advantageous when the inputs don't cover the entire input space, while the basis functions have compact support. In this case, the parameters corresponding to the basis functions will cover the data gaps and will be obtained via interpolation of the coarser models rather than from a random assignment. The model's training time significantly depends on the choice of the basis functions. The simplest functions, such as piecewise linear, require the least number of calculations, resulting in the fastest training time. As above, it's not necessary to keep the model's architecture constant throughout the entire training. One can perform majority of the passes through the dataset using the simplest functions and then switch to more elaborate functions with higher descriptive capabilities, such as splines, by resampling the parameters. Finally, it's not necessary to use all data records within one pass over the dataset. For records with small residuals, the update steps will not change the parameter values significantly. Therefore, within one pass, the errors can be saved in memory, and within the subsequent pass, only records with the errors above the predefined threshold can be updated. Depending on the choice of the threshold, such strategy can further lead to the noticeable decrease of the training time. As you probably know, when the Kolmogorov-Arnold networks are used now, quite often researchers adopt more than 2 layers of functions in the model. All results that I showed in the presentation up to now were obtained with the classical 2-layer model. This shows that even for high-demanding examples such as matrix determinant, the classical model is more than sufficient. However, one can introduce more layers, constructing, for example, a 3-layer model where instead of one intermediate or hidden variable, we have 2. In the same way, one can write a 4-layer model and so on. Contrary to popular belief, this concept is not recent. We have proposed it in our paper published in 2021. We did some work recently on multi-layer models, and the biggest challenge for them is finding a good starting point for the training. Therefore, we have developed an efficient pre-training algorithm for such models. It consists in training the model layer by layer. First, the classical 2-layer model is trained, the outer functions are disregarded, and the inner functions are then passed to a 3-layer model where they are fixed, while the second and the third layers are trained. Then the outer functions are again disregarded, and the first two layers are passed to a 4-layer model where they are again fixed. You can see that at each pre-training step, only 2 layers are always trained, and the upper layer is always disregarded. This pre-training algorithm results in an already good model, which is further improved by a traditional training of all layers simultaneously. Let me now show how the Kolmogorov-Arnold model can be used for data-driven solution of the PDEs. Omega denotes the domain on which the unknown function of the PDE is defined, gamma is part of the boundary of omega, and u is the unknown function. The PDE can be written in the implicit form. Function Li is non-linear with respect to the coordinates, the solution u, and the derivatives of u. The boundary conditions can also be written in the implicit form. We then assume that we have a set of boundary points and create a set of domain internal points, which are also called collocation points. The key idea of data-driven solution of PDEs is to assume that the solution can be represented by a machine learning model. In our case, we use the Kolmogorov-Arnold model. The parameters of the model are found by minimizing the residuals coming from the domain internal and the boundary points with the corresponding weights. Let's take a simple example of a PDE defined on a 2D domain of size 2 by 2. We can visualize the solution by plotting the slices of it at some values of y. Our model training method is iterative. Furthermore, we start with a random initial guess for the parameters. Therefore, it's interesting to see how the initially random solution changes with the number of iterations. Square symbols show the analytical solution. Initially, we see that there is a large spread around the true solution, but with the increase of the number of iterations, the convergence is observed. Let me now show an example from computational mechanics, solving linear elasticity equations using the proposed approach. In this example, I impose the displacement boundary conditions, and the analytical solution is known. We can again plot the slices of the solution for the displacement along the vertical and horizontal axis. Given the number of model parameters is sufficient, the numerical solution is visually indistinguishable from the analytical. It is more interesting to look into the structure of the numerical solution in the form of the Kolmogorov-Arnold model. The inner functions take spatial and/or temporal coordinates as arguments, and these functions are decomposed into the basis functions and the multipliers. When the basis functions have compact support, this very much resembles the finite element method. Changing the number of the basis functions corresponds to changing the mesh size. Therefore, we can investigate the mesh conversions. If we plot the error as a function of the mesh size, for the example from the previous slide, we'll see the convergence rate of 1.5. It's worse than of the finite element method, especially considering that the cubic spline that we use cubic splines, but the data-driven solution of PDEs is intended to be used in completely different scenarios than finite elements. There is interesting phenomenon when we increase the number of the outer basis functions, the mesh convergence is no longer observed, and for small mesh, the model overfits. There is also a convergence with respect to the number of collocation points. The increase of the number of collocation points beyond the number of the model parameters improves the result, but up to a certain point, after which the error doesn't change. So far, we have been talking about deterministic systems where the output is known exactly. In practice, deterministic systems can be affected by the noise, and the output may contain an error. In this case, numerical damping introduced in the model, in the method, can act as a noise filter. We have studied that separately and done experiments on real data, some of which Andrew will mention later. However, there are cases of intrinsically stochastic systems with aleatoric uncertainty. The output of such systems is a random variable, distribution of which depends on the system's input. For such cases, we have developed a probabilistic Kolmogorov-Arnold model, and the algorithm for its construction can be named divisive data resorting. The idea consists in creating an ensemble of models and obtaining statistical properties of the output from the ensemble of the outputs. Very schematically, the idea can be explained in the following way. Suppose we have some input-output dependency where the same input corresponds to some distribution of the output. We construct one model in the standard way by minimizing the residuals. It can then be called an expectation model. And then the data records are resorted according to the residuals and are subdivided into two even clusters over the median residual in the sorted list. At the second step, two new expectation models are built for each cluster. Then within each cluster, the records are again resorted according to the residuals, and then each cluster is subdivided into two clusters over the median residual, resulting in 4 clusters in total, for which new expectation models are built. And the process is continued in a similar way. Within the context of the Kolmogorov-Arnold models, we have proposed that the models in the ensemble have the same inner functions and different outer functions. We call it the shallow Kolmogorov-Arnold model. This is also related to the way how a vector output is modeled, which will be further discussed by Andrew. I will now show one example how synthetic stochastic data can be modeled. We consider data with a random output generated by a formula where randomness comes from a uniformly distributed random variables Cj. The formula is selected such that the distribution of the output varies significantly depending on the input. For example, for one input vector, the distribution density of the output has 3 maxima. I also plot the cumulative distribution function for this case here. When we construct different ensembles of models, we can see that for this input vector, the cumulative distribution is matched almost ideally. This is mostly the case for other input vectors, where only minor deviations from the exact cumulative distribution can be observed. However, for some input vectors, the deviations can be significant. But keep in mind that this example has been specifically chosen to be as challenging as possible, with significantly varying output distribution. Before finishing my part of the presentation, I would like to highlight that the Kolmogorov-Arnold model is a very powerful tool and it has a long research history. It dates back to the 1950s, when the exact representation has been derived, and 1960s, when it was improved. Over the past 30 years, constructive proofs for the exact representation have appeared, and approximate forms have been proposed. These approximate forms we now call models or networks. A relationship to neural networks has been investigated more than 30 years ago. It has been applied to machine learning tasks more than 15 years ago. A remarkable groundbreaking achievement of early 2000s is the publication of the model with the spline basis functions. This is exactly the Kolmogorov-Arnold network as we know it today, only with 2 layers. It has been applied to image decomposition in the late 2000s. Our own work published in 2021 focused on piecewise linear approximation of the underlying functions and on novel model training method. In 2023, we have generalized the approach to arbitrary basis functions and improved the model training method. In parallel to that, another model incorporating spline basis functions have been proposed and implemented by the group from South Africa. Only after all that, the Hyde paper from MIT appears, leading to popularization of this model. To conclude, I would like to say that our code outperforms all other codes known to us and neural networks. We have implemented it in MATLAB, C#, and C++. The latter can perform model training more than an order of magnitude faster than neural networks on large data sets, given that the models are trained to the same accuracy on CPUs. In the case of real data, there is no need to use splines. Piecewise linear approximation is super good enough. The Kolmogorov-Arnold model can also be used as a PDE solver. In this case, it has similarities to finite elements, as introduction of the basis functions with complex support essentially corresponds to the discretization in space and time. It thereby can bridge physics-informed machine learning and traditional mesh-based methods. It has mesh conversions, something that is not typically present in physics-informed neural networks. Finally, if you're interested more in this topic, please visit our website. Check out our paper on divisive data resourcing method, or the latest paper that has been just accepted to Machine Learning Journal. And of course, we have also GitHub repositories with all our codes. I will now hand over to Andrew, who will talk a bit more about some practical examples that we have been modeling, and more about our coding architecture. And we will.
Mikhail, maybe we should wait. Maybe we have some questions about the presentation before we move to the code. Or you prefer to cut
Should we take it after Andrew's part? Because then we can both.
No worries. I think anything worries. Okay. Thank you so much. It was a great presentation, and we're looking forward to this part.
I will stop sharing the screen.
Okay.
Okay. Now I share the screen. Okay. So I will speak about.
Have a question for you. So thanks for nice talk. And I am Youngkyu from Brown. It's just a simple question. Is your algorithm and code is GPU friendly? Nowadays, everyone uses GPU to train the neural network, not CPUs.
No.
But you just show the CPU result.
Yes. So it's not GPU friendly at the moment. So that maybe Andrew can expand a little bit more on that. So at the moment, it's a CPU code. At the moment, it's a C++ CPU code, and the MATLAB. So the MATLAB code doesn't use any linear algebra. So it's because in MATLAB, in MATLAB we actually have several methods implemented. So we have the Newton-Kaczmarz method, which I've been talking about, but we also have other training methods implemented in the MATLAB code. And one of them is Gauss-Newton method. And the Gauss-Newton method assembles matrices, and then you can use the MATLAB's capabilities to use GPU acceleration for that linear algebra. The MATLAB code, not the Newton-Kaczmarz method, but the other method, can be accelerated using standard capabilities. Yes, but not the Newton-Kaczmarz method as such. But we've been working on that. We actually have been discussing the way how we can transfer that to the GPU architecture. Maybe Andrew can expand a little bit more on that after his part, because that's what he was talking about.
I think now you can see my screen, right?
Yes, we can see your screen.
Yeah, that was Friday 13th. Here I quickly introduce some notation that I will use in the code. This why Mike already explained everything. So the single critical element, which is replacement for the neuron, is that one. So it's the layer expression is this one, multiple elements in a row. The layers expressed like this. So this is inner layer, this is input, intermediate goes here, another intermediate goes here, and the output. So this is outer layer, this is inner layer. So I will quickly explain why it actually works that fast. So what we are doing, so we find an increment for each individual element, neuron replacement, which improves the model, delta U. And when all functions are piecewise linear, what we need to do, we have an argument. We find the value, which the integer part of that value is index of linear segment. The fractional part of that value is offset from the left. And what we need to do, we have to move 2 points, only 2 points of piecewise linear function, up or down, and that is a very simple operation. Having this, I just told you how we compute index and how we compute offset, and this is what we need for just an individual function. And that is applicable for the entire discrete Urison operator, or another name is generalized additive model. So this is why that works that fast. So when we train for the layer, what we need to do, we use gradient descent, and we compute increments, having increments of the outer layer. So the difference we have to reduce. We increment inner layer, and F is a matrix of involved derivative for the layer. And since everything is piecewise linear, this matrix is easy to compute, and it's actually known when computing the output. So yeah, so if this is my video, and this is actually illustration of projection descent. So if you stretch piecewise linear functions, function values into vectors, we need each argument falls into linear segment, and we need to correct particular linear segment. And you see that this vector will be most having 0 elements. So different vectors for different records are pairwise orthogonal, most of them. And when they're pairwise orthogonal, we project the point from one orthogonal plane to another orthogonal plane. And this is why it converges that fast. So this is funny comments people posting under my video. They believe that in the future, all people are using Kolmogorov-Arnold, and we return from the future and introduce that video. So, which is wrong. We are not founding fathers of Kolmogorov-Arnold. It was invented before us. Yeah, now let's consider the code. I think it's obvious for multiple correlated targets. Since we have layers, the outer layers may convert everything into scalar or into vector. So it's pretty much the same thing. So the correlated targets are not any different from single target. Here for correlated targets, I have 2 illustrations. So one of them is medians of random triangles, and another areas for faces of random tetrahedrons. I can launch the code and then explain a few things. Yeah, you see, for obtaining of lengths of random triangles, it takes 0.3 seconds. And metric is Pearson correlation coefficient for all 3 of them. And then for obtaining the areas of the faces of random tetrahedrons, 22 seconds. And this is training sample for this is 500,000 records. And for these, yeah, 10,000. So, and my computer is slow. And let's navigate to the code. And the code is tiny. So the key element is Urison operator. Urison operator is that one square thing that is sitting in each layer. So the layer has multiple Urison operators. And you could see that the function, that multiple function, that these multiple functions is, the function value is actually a matrix. This is a model. What we need to keep also, we need to have limits for each individual function, and we also need interval, which is identical for this case. And you can see the entire code is like 200 lines. No third-party libraries are used. So here is layer. So we spoke about Unison, we spoke about layer. Now you can see this is the only code for the layer. So, and you can see here like list of Unisons. It's vector of the object. So we create them. And here we convert input to output, and we compute increments, and we update. So if we go to the code, here what we're doing. This is training loop. We take features and compute intermediate values. We pass intermediate values to the next layer and compute next intermediate values. And it also returns us the matrix of derivatives. It computes matrix at the same time. Then we go to the upper layer, output layer, and compute other modular derivative. Then we, having this output, this is our prediction. We subtract our prediction from actual target and get the first increment. Then we pass the first increment along with derivative. Remember that matrix multiplication, and we have other increments. Then we compute other increments. We go top to bottom. We go to bottom to top, and then top to bottom. It's like back propagation. And having the intermediate values and increments, we update 3 layers. That's it. And here we use validation record for the same thing. So we predict output, we find the error, we compute actual values, and we compute Pearson correlation coefficient. That is for multiple targets. Another thing I also used it for, another thing also researched is classification. So I tried MNIST, and MNIST is kind of like not a very good example because MNIST dataset is published for a very long time, and some people are very dedicated researchers, and they keep polishing the code until they beat the record. And when you try to compete, you compete with someone who may dedicate like several years of his life trying to tune this specific data set. And in our other examples, we generate new data each time. I mean, it may be a random matrices, it may be random triangles, but we generate data is new. And here is in MNIST, the data set is published and not changed. But anyway, so I assign target. One is assigned to the target that is actually to the class that is actually to the actual class, and 0 is assigned to all other classes. So we train. In the same way, we train for the multiple targets, and then the prediction is real value, and the maximum value is predicted class. And I use pixels as is. It was 784 elements, which is pretty large feature set, and I achieved 96% accurate result, 96%. It's usually what people have. So when people use pixels, directly pixels, they obtain 92 to 96%, and more than 96%. For more than 96%, you need convolution network. Convolution network is completely different. It's just like straightforward example. Speaking about, yeah, I have one more example. MIT article use LBFGS. Broyden, Fletcher, Goldfarb, Shannon. It took me a month to learn all these names. So I decided to compare. And I implemented also LBFGS code. I used, this one. So I used one C++ library, which was Okazaki library, C++. Yeah, and this comparison, that's it. It's not running all the time. My part functions in LBFGS, sometimes crashing, but sometimes now it's almost done. So in this is Kaczmarz method, and it achieved accuracy of 98%, 0.2 seconds. And this is LBFGS. It's concurrent implementation, and it achieved Pearson 94% for about 5 seconds. So this is the difference. So at this moment, Kaczmarz method is faster than anything we tried before. And speaking about divisive data resorting, I can also show a few examples. When we this article, we tried to publish it multiple times. When we sent to the journal for the first time, reviewer rejected because he said, like, all this is just theory. You didn't provide any real life example. And I decided to try a real life example. I modeled the sports betting. And in sports betting, you have to predict the outcome of the football match, and there is money price associated with your prediction. And when probability, and bookmakers set the bets and price according to probabilities that they estimate. And if the estimation is not exact, for example, they assume that was like 35%, but it's actually 35%. And your model is determined that it's actually not 25%, 35%, and you can bet on that outcome. And if you do everything right, that you can see winning money. And this is what about 15%, or from the amount we win 50%, 15% from the amount that we bet. And I have two examples. And then when we sent this paper to the second journal, the second reviewer said, "This is not casino, please remove that." So it's mathematical journal, and it's, oh my God, what we have done, we removed it. So, but this is example, this kind of like best real time application. So that means best real life application. So that means, like, if our model predicts something wrong, it wouldn't win the money, because the winning is based on more accurate prediction compared to what bookmakers provide. If we predict everything with the same probability that bookmakers provided, so there would be like zero balance here. By the way, bookmakers disallow to use artificial intelligence, so we didn't play because bookmakers disallow, and there are many. It's not surprising there are many people who try to use artificial intelligence for predicting sports outcome, and it perfectly works. So it's better than people. So it's known. That pretty much it's what I was intended to explain. And if you have some questions about the code, I can answer. And you can find everything. What I can recommend for usage in downloads, there are releases. And from here, you can download something that well tested and like reduced for end users, because many other codes are experimental. So if you need something working, you can use releases. That's pretty much it.
Could I also add quickly that it's also on GitHub? So the links are on the website, but also the repositories are on GitHub.
Yeah, right. Yeah, if you click, so you navigate to GitHub.
Great.
Yeah, website, and some downloads are from the website, but these on the website only experimental code, something that tested and verified, and more important, are sitting on GitHub.
Great. Thank you so much, Andre and Mikhail. Do we have any other questions from the audience? Maybe I have a question.
Okay.
Can you give us like a general idea, like in overall sense, what would, because could you please share your slides again, Mikhail?
Yeah.
Well, yeah, my slides. Yeah, right. 1 second. Share.
Mike, me or Mike?
No, my slides.
Okay.
So 1 second. Yeah.
Could you please go where you were explaining the algorithm?
Yeah, the algorithm. So
yeah,
just the algorithm for
maybe
the case.
Maybe in this one is good, or maybe in the previous one before you go to explicit like the one for Kolmogorov. Maybe the next one.
Okay.
Yeah, here. Here, like your ZQ is essentially your parameter, right?
Yes. Yeah. So ZQ is the parameters at the specific step of the iterative algorithm. Yes.
Yeah, and then what you get in the last equation is the iterative step, right? Like which would be your parameter at okay.
Yeah.
And here your L would be your cost function, right? Like your
No, here L is the specific equation for the specific data record. So this is the point, is that it's like very similar to the stochastic gradient descent, where you, in the case of stochastic gradient descent, you can use batches or you can just apply to individual records. So you have equation for each data record.
So you are not in this method you are not penalizing like the divergence, like how different is your prediction against how different is like the data that you're observing, right? Or how do you compute this L of Z?
So L is just the data record. It's just if I go so L is, if I let me one just quickly could get the pointer. So L is this difference between the real data point for each, like one data point. For one data point, Li is the difference between the real output and the model output.
So it's like a cost function, right?
It's a cost function for the specific data record, but it's not the cost function for the entire data set. Yes.
Okay, so it's like and then you have to compute the gradient per, essentially per point, right? So if I understood correctly, if you go back to the previous one where you were showing me where you have like this y minus y hat, this would be let's call it like an Li, right? Like,
yes, yeah, this is a lie. Exactly, this is exactly a lie. Yes.
okay. And then when you go, now can you go to the next one? Yeah, here. So here you would do one update per LI. So here
Yeah.
you. Okay.
Yeah. So one update per record, and then you do that update in the direction of the gradient with respect to the parameters.
But isn't that like a bit expensive, assuming that you have like a lot of points, like because you would have to compute the gradient of the network respect to a lot of points that you will have in your hands, right? Like, for instance, like let's assume that you're trying to approximate just a simple 2D function, right? And let's assume that you have like a grid of, I don't know, 100 by 100. It means that you have to compute the gradient of 10,000 points, right?
Yes. Yeah. But then almost all gradient-based methods will require that. So sometimes if you, for example, the LBFGS method, which Andrew already mentioned, and the comparison which we learned, so they don't estimate the gradient, they approximate it. So basically they iterate, so they sort of, the gradient changes.
Yeah, but the difference that then you consider the cumulative L, like the sum of all of L's, not per L.
Yeah.
So then it's a single pass. You only have to compute the gradient for one loss, and here you have to compute a gradient for each loss.
Yeah, but then if you think of no, the actual thing which I wanted to say about LBFGS is that you actually you don't compute the gradient at every step. So you propagate the gradient. So you essentially, it's like second method. You propagate the gradient. You have separate iterative scheme for the gradient. But then as for the gradient of the entire loss function compared to the gradient of like for a specific equation, the gradient of the entire loss function would be consisting out of the gradients with respect to each single point. You just kind of use the chain rule essentially, because if you take the entire loss function, like this, the sum of the squares for all data records, essentially it will be just evaluating the gradient with respect to the parameters at each point, and then you just essentially sum of them with weights.
Yeah, I agree, but the difference is that you only have to take it once. So the gradient, because in general, taking gradients with respect to your parameters is a bit expensive. So you would only have to do it once against the cumulative loss function against an opposite of taking it once per residual point. This
residual point. Yeah, but then it depends how you write the code. This is exactly the trick. Is that depending how you write the code, you can make it work. You can make it work faster, and especially in case of piecewise linear basis functions, you can make it work faster. And yeah, so it does work faster. And actually, one of the things which kind of you might think of. So we have compared two different methods. One of them kind of would be naive application of the Gauss-Newton method. So the Gauss-Newton is the standard method which typically numerical analysis students learn at the second year numerical analysis course. And the Gauss-Newton method, where you essentially calculate the gradient for the entire loss function once, and then you do the matrix update, it is faster for smaller systems. So when you have data sets of, I don't know, like 1,000 to 5,000, it is faster. But then when you have starting with data sets of 10,000, it is slower. So yes, the thing with evaluating gradient for the entire loss function once and then using it in a way like it is used in Gauss-Newton method, it can be faster for smaller systems. And actually for smaller systems, for let's say 1,000 records or like up to 5,000, probably the Newton-Kaczmarz it's not at its best. But then for larger systems, it is.
Oh, okay, I see. Oh, but okay, but yeah, thanks for explaining, because besides that part, I mean, it looks really similar to the normal gradient descent, and also it's still a first order method, right? Because you're truncating the second term.
Yeah, it is first order method. Yeah. Yeah, it is a first order method. But I can a little bit. I wanted to expand a little bit on that, but like for the sake of time, I won't do that.
Okay. And then what you're doing essentially in the next slide is you're doing this update step, but you have like one step for the inner functions and one step for the outer functions, right?
Yeah. But then if so this is what I show. Yeah. So if you have many layers, if you let's say have 3 or 4 layers, you obviously do that for each layer. So the way how Andrew showed in the code is done. So I keep my slides mainly about the 2-layer model, and obviously in the code for multi-layer model, it's done for each layer. So for each layer, you do this update of the parameters with this in the direction of the gradient. Yeah.
You use computation bottom to top or like from inner to outer, and then update backwards. So you first find the difference between model and prediction and the actual data, and then you navigate that delta, that difference backwards. And when you have difference for each layer, then you can use update of each layer. So this is similar to backpropagation.
Okay. So thank you. Maybe do we have any? Thank you so much for your answer to both of them. It was really informative. Yeah. Do we have any other questions from the audience?
Yeah, actually, I might have one. Hi, my name is Sasha Ransel from Brown, and I've been wondering, maybe you have been thinking about that already. Is sensitivity of training to initialization, because what you see in MLPs, for example, you need to be very clever with the initialization, and you have to tie it to the size of the network. Is there anything in analogy to that for Kolmogorov-Arnold networks? Because from what you show in your curves, it doesn't seem to be sensitive to initialization. What's your initialization actually in the first place?
Yeah. So I can answer that. So there is a short answer and a long answer. The short answer for 2-layer model, it's not that sensitive. It's like for 2-layer model, you basically use random initial guess. But for 3 and more layer model, they are very sensitive to the initialization, and that's why you need a pre-training algorithm. So this is the pre-training which I've been talking about. So without it, if we just use random initialization, even the 3-layer model really struggles. It gets stuck at local minima quite badly. But if obviously the same with 4-layer model. But if we use pre-training like this, where we basically train it layer by layer, and then we train within the pre-training steps, we train 2 layers each time and then freeze them. So we train 2 layers, disregard one, freeze the other one, and so on. So we can actually get already the model after pre-training. We can get the model which is actually quite good enough, and then we just improve that a little bit by doing the normal training. So yeah, so the multi-layer model is very sensitive, but there is a kind of a small bit there. There is a longer story related to the limits of the functions. I don't know how much time do we have. Maybe someone else wants to ask anything else. But so if no one actually wants to ask anything else, I will tell a longer story about the initialization.
I can add a few words to initialization. Let me share the screen quickly.
Oh, okay. Maybe I stop sharing.
Yeah. Do you see my screen?
Yeah, we see.
Yeah. Well, there are multiple ways of optimizing initialization. So one of them is train each addend individually. So if you see like one addend of Kolmogorov-Arnold, one addend, and we can train one addend for entire data set, and then another one, and use them all together, and that reduce time of training. So we need record by record training anyway. So, and here I show how it improves training for determinants 4x4 matrices. So it's 3 seconds. Normally, if for the random initialization, it maybe near 15 something seconds. So that means you can see it 5 times quicker, and 5 times quicker. So if it's 15 seconds, it doesn't matter. People can wait. But if it's 15 days or 3 days, that matters. So that means initialization matters. There are different ways.
Yeah, and you also, but by doing this, you're also in a better local minimum. So if you just start with random guess for 4x4 matrices example, you just so the results to which you converge, they are quite stochastic. So you can have good you can have like large errors and you can have small errors, but randomly depending on initialization. But if you start with a good initialization procedure, then you almost always will get good results.
Yeah, so it matters, and there's no single answer. There are multiple ways of optimizing initialization. Yeah, it depends on the model.
And is there do you use tricks like there's some tricks in MLPs that sometimes help with sensitivity to initialization, like scaling the initialization with the size of the network, or another one is batch norm layers that seems to help often in stabilizing training. Can you employ similar analogous adheres in CANs too, like a batch norm layer or a scaling with the size?
Well, we didn't really try that. We didn't really try that, but then there is kind of the limits of the intermediate variables, but that's something kind of maybe a separate story. We can kind of talk a little bit about that, but then it's a separate story. So the one thing which it's not related to the size of the model. So I don't think it's actually relevant in this case. So it's not related to the size of the model. No. In our case, no. The only thing is that yes, if you have a large model, you can't really just initialize it randomly. But for two-layer model, this is exactly what we do. So all examples which we did for two-layer model, which I showed, they have completely uniform random initialization for the parameters. So you just give the range for the parameters, and then it's uniformly sampled from a uniform random distribution. So but then yeah, as I said, so for three-layer model and onwards, you need to pre-train. But even with two-layer model, so you get better results when you train it addend by addend. So when you have like the technique which Andrew showed, that you just train addends separately and then assemble the entire model out of pre-trained addends. So that's better than the random initialization already.
Yeah, and even by pairs. So you take random pairs and train like not one addend but two addends. There are many options. As many as I try, I see that they can be customized for each particular data. So there's no single simple answer.
Yeah. But then maybe one more thing which I just popped into my mind. So the largest model which we tried had about 30,000 parameters, and that was a two-layer model with random initialization. So complete random initialization of 30,000 parameters. That was for a determinant of 5x5 matrix, and that worked fine. We didn't need to pre-train or do anything along these lines.
Okay. Yeah. Thank you. And I'm not sure if it is possible that it cannot be related to the size at all, for the reason that for MLPs, it might actually not, the same effect might not appear in CANs, but for MLPs, for certain types of MLPs, you can show that the convergence of the training dynamics does depend on the interplay of the size, the learning rate, and the width of the initialization of the prior in comparison to the width. And there might not be something similar in CANs, but I would be surprised if initialization is completely independent of the size of the network.
No, no, what is just maybe two things is that the training very much depends on the size. Obviously, the larger the network is, the longer the training process, of course. And then, yeah, so training very much depends. The training time and the resulting accuracy which you get is they are dependent on the size of the network. But yeah, so that's maybe like a slightly separate thing, not the initialization. Yeah, but then you mean what kind of best initialization we would finding best initialization? Yes, so that for two-layer model, like how would it depend on the size of the two-layer model? As I said, so we didn't really look in detail at that aspect, but then for the largest models we tried, we used random initialization and it worked fine. For two-layer model, as I said. So, but for three-layer model, you need to pre-train, of course. So this is where I decided, because by size, you might mean that you might think of the number of layers. So
yeah, usually I'm thinking of the width, but that of course
okay.
has to be set in relation to the depth. So for certain convergence behavior in the limit of width, you need to increase the width with increasing depth. So the deeper you are, the wider you need to go to observe certain approximate behaviors in MLPs. I don't know about counts. It might show some completely different behavior. So I'm trying to draw some analogies, but I think that's thank you. That was very interesting. I'm not sure. I might have one more question, but we might actually be out of time.
I would be happy to answer, but it's depending on like we can I don't know, we can have a formal and the informal part of the seminar, because I would be happy to answer any questions.
Yeah, maybe we can try to do that. Maybe if you have a short question, Sasha, you can ask.
No, I don't think it's a short question.
It's not a short question. In that case, do you want me to close the seminar and I can and then you guys can keep talking for a bit longer? Do you think that would work?
Works for me.
Yeah.
Okay.
And if anyone else has questions, I would be also happy to. We would be happy to answer.
Yeah, that sounds good. Does anybody else has any questions? If not, maybe I can stop recording and then I can close the seminar and then you guys can keep talking for a bit longer if you like the idea. Yeah, okay. Okay. Okay, thank you everyone for your time. Thank you so much, Andre and Mikhail. This was a really nice presentation. I think that it's time to close the seminar and until next week.